Hi guys, welcome to Learn Electronics Repair and another video sponsored by PCBWay.com. This is the little project we were working on last week. That was a previous sponsored video, and this little device basically determines the phase of windings in the transformer. So you can connect the primary to these wires, you connect the secondary to these wires, and it will tell you by lighting one LED or the other which end of the secondary is in phase with the primary. What that means is when the voltage on this end of the primary, the dot here, goes positive, which end of this goes positive. So depending on which direction you connect the secondary, either these two ends will be in phase, so they both rise and fall at the same time, or these will be in phase, rising and falling at the same time. The project after the last video, something strange happening with op amps, did actually work, but what I discovered and explained in that video is that we had a square wave on our op amp where we shouldn't expect to have one. I'll link that video onto here so you can see that, you can read the comments. There were various discussions as to why we had a square wave on an input of this op amp that basically wasn't connected to anything other than this variable resistor. So the variable resistor, one end is 5 volts, we proved it, we measured it, there's no square wave on it. The other end is ground, again, we proved it, we measured it, there was no square wave on it. But the wiper, which went to here, pin 2, not even stuck into the board, not connected to the circuit board, had a square wave on it. How can that be? This will just put a voltage between 0 and 5 on, depending on how you set it. Lots of people had suggestions about this, and on the live stream on Sunday, so this is the other channel that Detlef, myself and Carlos are on every other week on a Sunday, 5 PM UK time. We actually did some experiments with this. So we took the various comments that people made. One was to put a decoupling capacitor, 100 nanofarads, directly across the power and ground connection of the op amp. That should fix it. It made no difference. Another suggestion was that we just let the pin float and see if the square wave is still there. In other words, it's coming out of the op amp rather than going in from the potentiometer. And we found on the live stream the square wave was still there. So although the circuit worked, this op amp LM358 was putting a square wave on one of its own inputs. And it shouldn't really do that. The circuit worked, but it is rather unusual behavior for an op amp. If you look at op amps, this is not supposed to happen. So you can see the chip there. Hopefully you can read the markings, LM358. The next idea that people came up with on the previous video is the op amp is faulty. So we took another LM358, this one, and we put that on there. And it made no difference. Yeah, it made no difference. It did exactly the same as that one. This seems to have a different date code on, a different batch, even a slightly different logo, which suggests that one may be a genuine Texas Instruments and one maybe not. But they behaved in the same way. So both of them worked, but both of them had the square wave on pin 2. That's the inverted input. So it wasn't a faulty op amp. The next suggestion was that we tried a different type of op amp. So this is one that Detlef came up with. I'm going to see if we can see the part number on this one. MCP602. So this is a pin for pin compatible dual op amp with the LM358. And when we fitted this one in, the square wave went away. So it still worked, as this one does work, but this strange behavior had gone away. And the upshot of all this was that effectively these are a very old design op amp and they're just not very good. Okay, And this is a much more modern op-amp chip, and it works properly. I won't demonstrate this again because we did this on the live stream, and hey, I'd like you guys who don't watch it to watch our live stream, so that is still there. You can watch it after it was live, and for about the first 20 minutes or so, or 30 minutes, we're playing around with this, so get over there and have a look. So the name of the live streaming channel is The Electronics Channel. Yeah, inventive, that one. You can see that name on the screen right now, just there. So get over and have a look, and you will see that. I'll also put a link in the description to this video. So we now have this project that works. But Detlef and myself were discussing this, and I came up with the idea, well, couldn't we make this project using a microcontroller, effectively using one integrated circuit rather than 3? And Detlef, yeah, good old Detlef said, maybe. So that's what we want to do today. So we want to have a look to see if we can do this, if we can make this work with a microcontroller, and then work out if it's actually cheaper to do so. And we will make a PCB, we can upload that to PCBWay, but today, first of all, we're going to test the principle. Does it work? And talking of the man himself, here's Det.
Oh, we're already on. Okay, good morning, you good people, wherever you are, somewhere in the world, it will be morning.
Just the
I'm sticking with this perfect coffee from the little shop beside. If you ever go in Canaria, this is just commercials, go to the Manana bar, best coffee in the island, and the Cardidios are...
Yeah. And €1.30 for a coffee.
Yeah.
Creamy. Frothy.
From a Lavazza machine, a real Lavazza. So we cut this probably because we don't want to have this in here.
No.
Hey, people.
Maybe we will have that in there. Okay, guys. So what we wanted to talk about was the original design of this project. So what you can see is the schematic. We're down in the bottom corner, so we're not blocking part of the schematic. Yep. And this is the device. So I'll briefly explain how this works, and then Detlef will show you what we've come up with as an alternative using a microcontroller and why we think this is cheaper to build and easier. Okay, so we have a 555 timer chip. This is an oscillator. It generates a square wave, and that via this resistor, 100 ohms, drives the primary of the transformer we're testing. It might look strange that coming directly back to the op-amp on pin 2, but you'll see this point is actually ground. I think it's just the way the schematic's drawn. It may not be obvious if you're a beginner to this, but this is ground. Okay, so the transformer winding is between the square wave here and ground. These two diodes, by the way, if you're interested, these limit the voltage across the transformer to plus or minus 0.6 of a volt. Once it goes plus or minus 0.7 of a volt, the diodes conduct and they just take away the voltage, they short it out. So the op-amp here should have the square wave that you were sticking into the transformer on the input here, and that effectively comes through to the output, and you can see a square wave. Okay, the other side, well, if you look, we have two resistors, and this puts a fixed voltage on this input of the op-amp. And because the resistors are the same value as each other, the voltage is half VCC. VCC is 5 volts, that's the supply. So this has 2.5 volts on here. The transformer induces voltage into the secondary, and it puts pulses on here. And again, it feeds them out here, square waves, into this XOR chip. Now, what this is doing is a little bit of logic. And the way the XOR gate, it's called a gate, works is this. If both inputs are high, so they have a voltage on them, the output voltage will be low, 0 volts, okay? If both inputs are low, the output voltage will also be low. It will only be high if one or the other of these is high and the other one is low. So basically, if the signals are different, you get a high here. If they're the same, you get a low. And what this is doing is comparing the two square waves. So if they're in phase, They will both be the same, so they go high at the same time and low at the same time. The output of this will be low, and that turns this LED on. Yeah, through the 510 ohm resistor to ground. If the two inputs are different, so as this square wave goes low, this one goes high, so the output here will go high, and that powers this LED. So that's how it works. These capacitors, by the way, well, when this is switching, there are points in between where one goes high and one goes low. You may get a little spike here at the switching point, and these just smooth out those, so the LEDs don't flicker. So that's how the system works. The variation we made, by the way, was on pin 2 here. The original version wasn't working properly because pin 3 was always above ground. This wouldn't switch properly, so we put a potentiometer here, effectively resistor to VCC, resistor to the ground. Basically, we recreated this and we put it on pin 2, and then it worked.
Yeah, and then we changed the op amp to a MCP 602, I think.
Yes, it was, yeah.
And, this is not the ideal op amp for that application. The 602 is a rail-to-rail, so it can switch really between VCC and ground, and it's designed for single supply voltage. And this was a better choice. And the LM358 is an old design. I think it's about 40 years old, so don't expect high-quality outputs here.
Yeah, and this is why we had a square wave on pin 2 that we couldn't explain.
Yeah, there was some nice things we did in the live video here, and we had some great discussion with you people out there while we were talking about this in the first one. And you decided you want to go the full way, and you said, okay, let's do the advanced version with a microcontroller. So you are guilty here. Okay,
so let's have a look at the schematic that we came up with.
Let's go for that.
Let's go for this. So this is actually the microcontroller version, and here's the schematic. Now, I just explained how the analog one worked, and Det was very much involved in the design of this one. So over to Det. Can you tell us how this works?
Well, I think I can. I hope I can.
Okay,
let's find out. All right. We had some discussion, and if you watched the first part, you probably get how this will do this work, because we discussed about 90% there, and just went from there, just drawing stuff up. So I know a few people of you said, okay, can we do a nano for that, an Arduino nano thing? And we were going for it because we like them now, for this little naked chip things. And
not naked chips again.
Not naked chips.
Oh, it's okay.
Black bars. Black bars.
Yeah. We actually proved, by the way, on YouTube, you can put naked chips.
Yeah.
You don't need little black bars to censor them.
Yeah, and we don't get strange commercials, I hope. Naked chips.
So we have a naked chip.
Yeah, it's going to be an 80 Tiny. You guys probably know this one. We use this in Mr. Bleep. Mr. Bleep uses the same one, and one thing we said, okay, we want to keep this beginner friendly. Even if I have the microcontroller, we want to go through all the things. So everything you see over here is through-hole components, so easy to solder.
And easy if we put an IC socket to take the chip out and program it if we wish. Yeah. Or when we've burnt one out, we can just put another one in.
If it blows up, you can easily exchange this.
Okay. So is this chip very much like the ones they put on the Arduino?
Yeah, we're using an Arduino IDE to program this.
Okay.
So all you people out there, there's no hurdle there yet you get to, okay, I need to learn some Atmel start things. Atmel start doesn't have the 80 Tiny.
No, you just effectively use the same IDE, the same way you would program an Arduino, you just program this.
Yeah, when you're at home with the Arduino, we probably do a download with the IDE, with the software, with the final software that we're producing here. And you guys can simply download this, build a little programmer. I don't have one here right now.
Okay.
But we'll link to a video where you can see how a programmer works for that.
Okay.
And if you don't want to build a programmer, you can use a nano and some wires. And it looks horrible, but it will do.
It works. Okay. Yeah. So what do we have on the schematic? Apart from the microcontroller?
The brain, of course, and there's a decoupling capacitor. You remember decoupling capacitors? Yeah. I had a little bit of a rant last time, because do decoupling capacitors everywhere you can go. This is just for keeping the voltage around the little chip stable while it's doing its thing.
So this capacitor is mounted as close as possible possible to the chip.
Exactly.
And it's just connecting from power to ground.
Yeah.
Yeah.
Yeah, you do this normally on every digital chip because you don't want to have some little frequencies up
Okay.
there and then they get into ringing and oscillating and destroying itself. So we don't want to have this.
Okay.
Over here, there's not much to see. This is the voltage in. We need some way to get some voltage in
And
here.
this will be 5 volts, the same as the original version of this?
5 volts, yeah.
Okay.
We could go lower, but we can't go any higher with that.
Okay.
5.5 is the max the ATtiny can handle.
Okay.
So 5 volt is fine. We can use the USB thing.
Uh-huh. Oh, yeah, sure.
Yeah. Let's go to directly to the output before I go into the analog part over here. So we have 2 LEDs over here, LED 1 and LED 2.
Uh-huh.
The in-series resistor is just for limiting the current, and these pins come directly from the little controller over here.
Okay, so the controller can actually power the LEDs directly.
Yeah. This is capable of doing some, I think 10 mil max. So and we're going for
330 ohms. Yeah, it's about 6 mil.
Max.
6 milliamps, something like that.
Yeah, way
6, 7,
way
yeah.
low. So
Okay.
no problem for the controller. These are software controlled, of course, and they will lit up when we are in phase or if we're not in phase. I don't know which way around right now, and we'll figure out while we're building this stuff.
Okay.
All right, there's some analog stuff down here, and let me see if I can get this in shot while we see the thing over here. I'd start with the input state, or with the primary stage of the transformator.
Audio transformator.
Transformator.
Is this German thing?
I think it's a Austrian thing. With
Oh.
Arnold Schwarzenegger.
Audio transformator.
Yeah, the transformator. Yeah, special powers, transformers.
Oh, there we are. Yeah. So this is the transformer which we are testing to find the phase of the windings.
Yeah, it is. This is the footprint I came up with when I was looking for a footprint for that. This was the one that was handy somewhat, and I didn't want to mess around. Maybe we change this later, but for now, this is fine. This looks fine on the layout too. So I'll stick with this. So
Okay.
primary, secondary. And we're going to pulse this thing. This is something the NE555 did in the original design. And
yeah, it was oscillating a square wave about 1.6 kilohertz.
absolutely, yeah.
Okay.
And we're going to do the same with our little controller over here. So there's pulse out. You find this over here.
Okay. So
And this goes into this little MOSFET with 330 to the gate and strapping down the gate to define potential without this thing being active.
yeah, this is just to stop the gate floating on the MOSFET, basically.
Yeah.
So are we going to use the same frequency as the original one?
Yeah, we can. Since it's a controller, we can switch frequencies as we want.
Oh, okay.
Yeah.
So the original one, the NE555, there's a resistor and capacitor which sets the frequency it oscillates at. So what you're saying with this one, because it's a microcontroller, we can do that in software.
We do this in software, yeah.
Oh, that's interesting.
We will be interesting. We will be able to sweep the frequencies there. So let's see how this turns out if we need to do this. This could be a thing with a transformer that we can go higher frequencies, higher efficiency.
Yeah, okay, so maybe this will test a wider range of transformers than the original version.
Yeah, could be, yeah. But
Okay.
this is something we need to figure out while this is going, and this is why you guys are here. 'Cause This is live. We're doing this right now. We didn't test this before. This is development here.
Okay.
So we're going for the controller itself couldn't drive the primary coil. This won't fly. This will burn out the controller. So we selected a little MOSFET here, and we went for something that you probably have lying around, a 2N7000.
Oh yeah, and this is actually true, guys. So Det came in with a little bag of MOSFETs. That's what we got there. He says 2N7000s, they're really commonly used in circuits and projects. And I said, well, you must be right, because I went into my drawer of components and got another bag of the same out, bought independently. I said, that's what I found. I Googled it. What should I use? 2N7000s.
Yeah.
These were about, there was something like €1 for a bag of like 50 or 20. They were very cheap.
They are.
I can't remember. They were extremely inexpensive.
Yeah. If you want to have some MOSFETs lying around that are in through-hole, 2N7000 is a great choice. This is logic level compatible, so it will run fine from the Arduino, from the ATtiny.
Yeah.
And the 300 ohms resistor over here is just the thing you do.
Yeah.
Yeah, you normally put something in front of the gate. If you want to go nasty, you can skip R2 and put drive this directly from the CPU.
Yeah.
But normally you don't.
Normally you don't, yeah.
Yeah.
So we have a diode in here as well, and this R347 ohms. What are these for?
This one is a flyback diode.
Oh, okay.
This keeps. You can explain this better. You better with the analog stuff.
Okay, so yeah, so with this D1, when we pull current through the transformer winding by switching the MOSFET on, the current builds up a magnetic field in the winding, and it induces a magnetic field into the secondary. That's how we get an output from a transformer. But when you switch this off, this end effectively suddenly becomes open circuit. The magnetic field has to collapse because there's no more current flowing through. And when it collapses, it actually collapses very rapidly and puts a high positive voltage on here. So this is doing two things. One, it's preventing the high positive voltage from damaging the transistor that's driving it. That would depend on the rating of the transformer, of course. But the other one, if you didn't have this diode here to take away the high positive voltage, and look what it does to it, it just shorts it back to the other end of the transformer. If we didn't have this, what would happen is the magnetic field would collapse, we would get a high positive voltage, and then effectively that positive voltage would flow back through the transformer the other way, and it causes it to magnetize in the opposite direction. And the voltage on the end here, instead of like sort of just switching on, off, it would switch up, down. So you go fly back the other way, fly back this way, and it's like something on the spring. It oscillates until it effectively settles to zero.
Is this called ringing?
Ringing, yeah. But the problem with that is also that the secondary will get the ringing. So instead of getting a square wave coming out, we'd also get a ringing waveform coming out as well. And it'd probably be very difficult to determine the phase because of the ringing. So that's what that does.
Nice.
Yeah, this one, look, I'm assuming this is just to limit the current that flows through here, the maximum current, in case this gets switched on permanently for some reason.
Indeed it is, yeah.
Yeah. So what we have, 5 volts, roughly 50 ohms, that's about 100 milliamps maximum current. So even if we make a mess up in the software for some reason, or we switch the MOSFET on for longer than it takes for the coil to fully magnetize, because at that point this becomes a short, that will just limit the maximum current.
Indeed, yeah.
Okay.
This is the idea behind this. R3, the value of R3 is currently arbitrary. I have no idea what we're really going to use. With 100 mil, we'll probably be fine.
Yeah.
There will be no current flowing because there's no load here. And this is something we have to experiment with.
Yeah.
Probably get this a bit higher, a bit lower. I don't know yet.
This on the original version with the 555 was a 100 ohm resistor.
Yeah. And we probably try this out. This is something figuring out while we're doing this stuff.
Yeah.
Okay, primary side is done, I think.
Yeah, sure, yeah. So we have some more stuff on the secondary.
Yeah.
We have more diodes.
Yeah, we have more diodes, and the secondary only has diodes, yeah.
Okay.
This is a clamping thing here, over here. So I'll clamp down the voltage, this is ground, and clamp down the secondary voltage to about 0.7 volts, 0.6, you normally say 0.6,
So
0.6,
if this voltage here goes above 0.6 or 0.7, this diode just shorts it out. And if it goes below, this one will short it out. But if we put a square wave in, it's not ringing, we should just get a positive voltage here. But you've got this, yeah?
Yeah, indeed, yeah.
So
this is a Schottky.
Yeah, that's why the symbol for this diode is different from these. Like a little S, I always think. Yeah. So what this is for, I can see myself, is so that the current can only flow in that direction. So this can only ever be positive compared to ground.
Indeed. Yeah.
And the reason we use a Schottky is because the voltage drop across is very low, about 0.15 of a volt rather than 0.6 of a volt. So that means that if we have a very low voltage coming out on the secondary, due to the type of transformer testing, hopefully we'll still get a voltage coming out here.
Yeah, we tested this out on the live stream, and if you didn't watch it, I think Richard will link this there. And we simulated these output stage on fault start, and it came up with a slightly negative voltage on for the input, some 3 microvolts or something, so very, very low. And
what was that software called?
Fault start. This is a online in-circuit simulator.
Oh, okay.
I tried, by the way, if Carther, if you're watching this, I tried the multi-sim thing, and this is limited to 5 components in the free version. And fault start, you can put a really big design in there and doesn't cost a thing.
Well, in that case, we'll give you guys a link to that as well. So in the video description, you'll find a link to a simulated. This is simulating analog electronics, yeah?
Yeah, it does, and it simulates digital.
Oh,
yeah, and it's free, and it's free, running in your browser. Jesus, crazy times, I tell you guys.
It is. So once we have this working, we have pulse in here, and that goes back into the microcontroller.
It does.
So what we're doing is we're comparing the phase of pulse out, which we drive in the primary with the phase of pulse in, which is the signal coming back.
Indeed.
And saying, are they in phase like one LED, or the out of phase like the other one?
Yeah. And this is going to be interesting because the audio transformator will have a phase shift in it anyways, because coils do a phase shift like a capacitor does.
Yes, we were discussing this. So when we first came up with this idea over breakfast the day afterwards, I said, Deb, we might have a problem with this. And the problem I thought, which may or may not be a problem, is that on a transformer coil, you get a phase shift, and I don't remember exactly all my analog stuff because it was mathematics. I basically know what it does. So I believe the voltage lags the current by 90 degrees, or vice versa. One lags the other. Yeah, or the current lags the voltage by 90 degrees. And the current is what is effectively inducing the voltage into the secondary, which means that, as far as I understand it, the voltage in the secondary, the square wave, will be shifted by at least about 90 degrees anyway. So we can't just say, okay, well, if this is 180 degrees out of phase with that one, the winding is connecting one way around. If it's in phase, it's the other. I think we're going to find something different. So we're going to have to build part of this at least.
Yeah, we're going to start. We're really going to do this live for you guys. This is a design episode. We're not tested this out. And we're starting with a breadboard thing. And we're going to, I think we start with the primary stage. So get the MOSFET in there, get some resistors. I do the programming for the 80 tiny.
We'll do this.
Give us a square wave, and then we get the oscilloscope out. And
and have a look to see what's happening on the secondary.
What happens there,
Okay.
This is what we're going to do now.
So we have a plan. So get first steps then. So we'll get us put together on the breadboard, and Det can get messing around with code. Oh, sorry. Det can make expertly optimized code. As he always does.
I'll get back to you for that.
That's right. Well, guys, Det's been writing a bit of code, and I've been putting this together on our melted breadboard. If you didn't see the live stream a few weeks ago, then watch it. So this is the microcontroller. The yellow wire is pin 3. I don't know how clearly you can see, but this is the MOSFET tucked in under here, and this is the
330. Yeah, this is the 330.
Looks more like a 33 to me, but it's what I grabbed. It's a 33 or a 330. I think that's actually a 33.
Said it doesn't matter.
Said it doesn't matter. Yeah, obviously it was just in the wrong place in my little stash. So I'm actually monitoring on the scope. You can see, if I just zoom out a little bit, the scope probe here on the yellow wire. So that is the output from the CPU. Now, when we first connected this up, it looked like the scope wasn't triggering. It was a bit all over the place. And I thought, is there a problem with the scope? And then Det said, put a decoupling capacitor. So we put a decoupling capacitor. You can see here a little capacitor, ceramic capacitor between the 5 volts and the ground. Yeah? Watch what happens when I remove this capacitor. So that isn't the scope not triggering, that's the microcontroller jittering.
Yeah, it's jittering. It looks like, look, I just saw that. It looked like a reset. It looked like a complete reset.
Put the capacitor back on.
Yeah.
So
this is the first time I see this so explicit.
Yeah.
Yeah. And this is why you're using decoupling
capacitors.
Thank you.
Yeah, I've never seen that demonstrated so well as that ever. Guys.
Okay, this is of course a complicated situation. We have wires, and there's a 1
kilohertz
thing in there, and
put it back in.
This is enough to get the little CPU completely. Oh, now you made it completely mad.
Back again. Okay, so yeah.
So lots of antennas here, and we're pushing some current because the transformer is already connected. So
and it says we're drawing 40 milliamps on the power supply at 5 volts.
Yeah. So the 47 ohms was quite right.
Yeah,
I think
47 ohms is just right. Guys, decoupling capacitors are not overrated.
No, they aren't.
These are not overrated. So hope you like that. We like that. So I can now attach the other scope probe to the transformer. So this is our transformer. So if I clip on here,
You're a bit out of shot.
I'm a bit out of shot.
Yeah, just a bit.
Better.
Yeah.
So we go on to the secondary of the transformer. Okay.
Mm-hmm.
And there, on the cyan waveform, that's the output from the transformer. Now at the moment, I haven't connected anything else. So there were some clipping diodes. We're going to put them on a little bit and see if it makes a difference. And there was the Schottky diode. But that's just the raw output from
This looks good.
the transformer, yeah? And you can see that the voltage rises.
Yeah, it's in phase.
Yeah, it's in phase. So as this rises, this also rises.
Yeah, and it's pretty much spot on.
And it's pretty much so. This business of being 90 degrees out of phase doesn't seem to be the case. Watch what happens if I reverse the polarity of this oscilloscope. So I'm now the other way around on the winding. And look, it's now out of phase. So when this is low, this is high. When this is high, well, it's above a certain point. So, Jet, do you think the microcontroller will happily be able to distinguish between these two?
Well, not
conditions?
with this waveform, but we have to check what this does when we have the Schottky and the double clipping diodes.
Of course. Okay, so I'll now add the Schottky diode, the clipping diodes, and let's see what it does then.
Yeah.
Okay, guys, so I've now attached the Schottky diode and the clipping diodes. They're down here. Looks a bit messy on the breadboard, but that's where they are.
This is why I hate breadboards.
Yeah, so I have my scope probe attached to this also. Now, there's no ground on this part of the circuit, but because this scope probe is effectively connected via the scope to the other one, and the clip on the other one is connected to ground, this effectively is grounding this end via the scope probe leads, basically. So we'll just zoom out a bit. You'll see I have the transformer here. And if you look at the waveform now, it's similar, but this is much flatter. Yeah, so you can clearly see this is an antiphase. There, yeah. And then when this goes high, this goes low. Let me reverse the winding, okay, on the transformers.
Let's do the same phase.
Let's do the same. So that seems to be an antiphase. Is that an antiphase?
Well, it's still an antiphase.
What's happened here?
Oh, what did we do there?
I don't know. What did we do here? What did we do here?
Interesting. This is my diode in there that always does the...
Oh! So the Schottky diode is always conducted. No, but it shouldn't affect the phase.
It shouldn't, no.
Take this off. Put this on the other way.
Oh, now
it's
right.
an anti-phase. I must have had a bad connection or something stupid going on.
No, it's in phase. This is in phase.
Now it's in phase now.
Yeah. Great.
So, yeah.
Okay.
So we can clearly see now that when this one is low, this one is low. When this one's high, you get like a peak. So this here, this is effectively the transformer starting to conduct the inductor. So the voltage across the transformer decreases. Yeah. Can our microcontroller determine between these two conditions, you think?
I think it can, yeah. We are going to use a ADC for that.
Okay.
And I think I'm looking for this sharp spike there. And then I can tell on which side of the phase we are now.
So we've proved the concept. We get a different waveform. The only thing is now Det will have to go away and work out how to code this to effectively write the correct LED on the waveform. Okay, so for today, I think we can call that a bit of a success, yeah?
I think so, yeah. The hardware seems to work. If you're looking at the VPP for channel 2 and think, okay, there's coming 2 volts in there, it isn't. The probe is set to what you said.
Yeah, so this probe on the secondary is actually set to times 1 on the probe, and this is set to times 10.
So we actually getting 2 point something volts in there.
Yeah, about a tenth of the voltage in actual fact.
Can you disconnect one of the clips from the transformer, please?
Which one? The primary?
It doesn't matter. It doesn't matter. Simply disconnect this.
Okay, so
Yeah. Let me see how this looks then.
it's like noise.
Oh, there's a lot of noise. We maybe have to drop in a resistor over there because I wanted to use the input of the ADC. If I don't see any fluctuations on the ADC, I want to detect this, and I can detect this, and then I know, okay, there's nothing connected. And we're floating like that. That could be a bit hairy.
Well, there's no reason why. I mean, at the moment, what we're actually doing is the white wire on the transformer. This one is actually connecting to ground via the oscilloscope probe. So this ground clip on the scope is connected to the other ground clip on the scope, which is there, yeah? That's this one, that's the green wire.
Yeah.
So that's what's making the ground. I think in our version, I think we should ground one end of the secondary.
Yeah, we're going to do this anyways, and in the schematics it was already in there to
It was,
this.
okay, let's have a quick look at that.
Yeah.
Okay, yeah, so you can see on this version, one side of the transformer is grounded. I'm effectively simulating that by using the scope probe leads.
Indeed, yeah. I think we drop a little resistor across the output here, yeah, right there. Something about 47k or something, to have a defined potential if this is open.
Do you think we should just pop that on there now and just have a quick look to see?
Yeah, let's find it out.
Okay.
Yeah. You want to see a different frequency for the transformer?
Oh yeah, we can also try that. So let's just, before we do end this video, first of all, we'll put a resistor so there is some sort of load. I'm not sure this will make a difference, so let's see how very wrong I'm proved. What do you want, a 47k?
47k is fine, yeah. This is the same we're using somewhere else, and so this keeps component count.
Not even a 4k7, no, 47k.
47k doesn't matter. I just need some defined.
So all you want to
potential
actually
there.
do actually is to put this across the transformer.
Across the diodes.
Across the diodes.
Yeah, the 4148.
Okay, let's just go back to the oscilloscope. Okay, there's the oscilloscope. So I'll now put a 47k resistor across the diodes. I'll do this while it's running.
Yeah, sure. That won't matter.
There. Oh, that's my finger touching it. It does make a difference.
Oh yeah, there's a slight load there.
Yeah, it goes like that.
Okay.
Do you want me to reverse the polarity on the...
I'm not sure if I like this.
No, I'm not sure like that either. I think it's better like that.
Yeah. I think so.
Yeah.
Interesting.
Okay. And the other thing, let's just try is a different frequency. So we're at 1 kilohertz now. What would you like to change to?
Yeah. Got you 500 hertz in this one.
Okay. One moment, guys, while I switch the chip over.
Yeah. Let's see if the
Transformer.
waveform looks better, looks more square.
I'm thinking what will happen is the more you increase the frequency, the higher the efficiency of the transformer, and the more output you will get. Can you go? How high can you go? 10 kilohertz.
I could go 10 kilo.
Okay.
I'm using 2 now. And,
So here's 500 hertz.
okay, this is bad. This is even worse.
Okay, let's try a higher frequency.
Okay. Yeah, just getting you to K.
10k.
I've gotten 2K in here.
Okay, this one's 2k.
Yeah.
And then we'll go for 10. How fast will that processor actually run?
For the tone thing, I can do something that's about 20K. Or say 15K.
Okay.
But I'll need to keep an eye on the ADC.
Oh, that's better.
Sexy.
Shall we have? That's more like a square wave now. Shall we reverse the polarity on the secondary again?
Please do.
There.
Oh, this starts to look like a square wave.
This looks like a square wave. Okay, that's 2k. What
right.
else are we going to now?
Let's go 10K. Here's a 10K machine.
Okay, 10 kilohertz. Let's see what this does. Let's go.
Okay, of course, this is too fast for the scope now.
Now we have a square wave. Oh,
Wow.
so 10 kilohertz, and then we can reverse the polarity. I have a bad connection.
Yeah, you have.
That's in phase.
That's in phase, and it's definitely in phase.
Like a square wave.
Yeah.
And we go the other way. And that's out of phase.
Yeah.
And definitely
Wow.
square wave. So guys, 10 kilohertz seems to be like a sweet spot with this.
Yeah.
I doubt if we went any higher we would get any better.
Yeah, the higher the frequency, the better.
Yeah.
And this is what we take away from this. Yeah. So the highest frequency I can get from the CPU. I'm running at 8 megahertz. We probably won't get any higher than 5 to 10 kilohertz.
Yeah, because we have to do the monitoring as well on the ADC. Okay.
Yeah, this will take all a bit of time. I'm writing down a loop now, and let's see what happens then. But this is a really interesting thing here.
Yeah, this is. So I think we've actually learned some stuff here, guys. I mean, ourselves, we were amazed by the difference that little decoupling capacitor made. What happens if I take it off now?
Don't crash my CPU.
Oh,
it doesn't do anything anymore.
It doesn't do anything anymore.
Now it's gone really mad.
So, right, what do we learn? A, decoupling capacitors, fit them.
Never overrated.
B, we don't seem to get a phase shift just by having a winding on a transformer.
We were talking about this. This isn't on camera because we were just discussing this. And I thought you have 2 coils in a transformer. Primary is secondary. And if a phase shift is there and you have a phase shift on 90 degrees on one, and have a phase shift 90 degrees on the second one, it comes up to 180. Is this true?
I don't know, because that would suggest that when we see the two things in phase, you're actually out of phase, and when we see them out of phase, you're actually in phase.
Yeah, because normally I would expect there would be a 90 degrees shift somewhere, but it isn't.
Guys, comments?
Yeah, please, swarm intelligence out there. Let us know.
And the other thing we've really come away with is just how much the frequency changes the waveform that we see on the transformer.
Oh yeah. This is really interesting. I never saw this before.
No, I've not seen this done before.
Yeah.
So guys, a little while later, Detlef has cooked up some code, and this is the working version.
Yeah.
So
you know what took us the longest? Me realizing that the output stage on the board isn't connected to the CPU. I was fiddling around half an hour there, and without Wi-Fi on the output stage.
So basically, we were trying to fix the software when it was hardware.
Yeah, that reminds you, always check your circuits if it's already done. And we only measured this, we never connected it back to the CPU.
And also somebody didn't connect one of the LEDs to the right pin either. And it wasn't dead.
Wasn't me.
But anyway, this is now working. That's the upshot of all this. We can put it into a position where you can see it. We have the 2 LEDs. Just zoom out a little bit. You'll see this is now powered off a USB. This is into a laptop in actual fact. So if we disconnect the secondary, you'll see the LEDs go out or maybe just flicker slightly. Connect it back on. We have 1 LED lit. If we reverse the polarity, if I can get the
you see there's some interference coming in.
I had my fingers on there.
Oh yeah.
So that's the other LED lit. So quite literally, if I go across these two and keep my hand out of the way, we have 1 LED lit, other way, other LED lit. So this is actually working at least as well, and I think probably better than the analog version.
Yeah.
I worked out that the cost of the chips, if you were buying chips like in sort of 10 555 timers, 10 LM358s, and just a couple of the 4030, the whole cost of the components was somewhere around $2. And Detlef thinks the microcontroller version, there isn't that much difference.
No, there isn't that much difference. Yeah.
Considering if you were buying the PCBs, it cost you €5 from PCBWay.com to get 5 PCBs plus the postage. But the one thing we will say, this version is easier to build on Breadboard.
Yeah, it could be built on Veroboard without any problems, all through components, and the circuit diagram is pretty easy. We didn't change a lot for it. You see this in a second.
Yeah, so that's the one working. So what we need to do now is we'll have a look at the PCB layout, and we'll look at the schematic again. And then, as we have been doing recently, I'll pass this over to Detlef, who's going to make a follow-up, or rather a sister video to this one, a companion video.
Yeah, a sibling video.
A sibling video,
nice.
Where Det will explain the code. You say it's only about 50 lines of code.
Yeah, this is easy to follow, guys. Don't panic, this isn't complicated. I thought this would be way more complicated, but I cut a few corners there, and I'm getting away with 50 lines of code, and it's nice written code. Okay,
yes, I'm sure what you guys who are interested in the code, you can go over to Det's channel and have a look. So we're going to have a look now at the layout.
At the layout, yeah.
Okay.
Let's go to the schematics.
Let's go to the layout and schematics. So here is the schematic. Detlef only made one change, which was a resistor here. So I'll let Det explain to you why that is, and then we can look at the actual layout of the PCB.
This is actually when you have an open line there, because we are high impedance there. The microcontroller is high impedance, and if it's open, well, there's nothing on these pins. The ground goes through the diodes, and the diodes are not connecting there. So I needed something to keep the input pin low, so I don't have interference on that.
Basically, because normally at like less than 0.6 volt, these diodes are not conducting. Nothing's conducting, so this is floating around.
Yeah, flapping in the breeze, like
Flapping
Dave Jones
in the
says.
breeze.
Yeah.
Okay, so that's the only addition to the actual schematic and the layout.
But we have a
That.
PCB for that. Yep.
Okay.
Yeah, this is the whole thing. This is a proof of concept. That's what POC means. Transformator dot convention tester POC. And yeah, LED 1 and LED 2, the transformator you see primary, secondary on the top side. And these are resistors. The resistors are standing up. You know, you see this when we do the final PCB for that.
Okay.
Yeah, one big part for the 100 nano. We learned that is necessary.
Okay.
Yeah. And yeah, this is all. So you see, this is a very tiny PCB. We get away with about 30 by 40 millimeters.
So is there no space even to fit our names on this one?
I think it's on the back side.
Oh, of course.
And since this is the proof of concept, I normally don't go for 3D over here.
3D.
Yeah. And then you can move it around.
Oh. Det.
Yeah, I signed my name.
Yes. Det and Lady Electronics Repair. Okay, so there is our little PCB with some of the components already inserted.
You know, again, I think this is pretty much done, this project. This didn't take really long. It isn't my nicest PCB. People with some HDSD will probably scream now at the screen and tell me, oh, get the transformator in the center and the proof of concept PCB, don't matter. Maybe if we get really bored, we do this nicely, but we normally don't get bored, right?
No, not normally. Not normally. I'm just looking, where is the Schottky diode?
The Schottky is the DO41 you see right under primary, yeah.
Oh, and this, so we have the two back-to-back. We have the one for the flyback diode on the transformer.
Indeed.
And that is the Schottky.
Yeah.
Okay, guys, so...
And from there on, the resistors are mostly 330 ohms, so for the LEDs, and for the MOSFET is 330, and I use 47 for the MOSFET ground connection and for the flapping in the breeze pin, so we should be fine there. So the component count is really low, and mostly we use the same components there.
Yeah.
Oh, this one's nice. 47 ohm for the current limiting in the transformator. So yeah.
Transformator.
Transformator.
Oh, I see that. It says 47.
Yeah, that's a 47 in the T. Yeah.
In the T.
Yeah.
Yeah. Okay, guys. So hope you enjoyed that. I think we did. Found some very interesting things making this video.
I think so too, yeah. And we learned something today. Never trust that the output stage is connected without checking.
Yeah. Never expect it to work without a 100 nanofarad decoupling capacitor because the power supply to the CPU.
That was really interesting, yeah.
Yeah. And transformer winding phases don't always do what we thought they might.
Indeed.
Okay, so
learned something today, mate.
We learned. Okay, so one thing left to say, and that is, bye nerds.
Bye nerds.
Ciao for now. What the? See you, guys.
See you guys.